Hello everyone. Now let us express the instantaneous angular momentum of a projectile launched at a velocity u at an angle of theta about the point of projection as a function of time. Let us see how we can approach this question as a function of time. So now let us see how the image will look at some value of time, at some value for t. Let us see how this will look. So let us assume a projectile is somewhere here. It follows a parabolic path. I launch it at an angle of theta with a velocity u, v or u. So what I'm going to do is I'm going to use angular momentum as mvr sine theta. Yeah. So this is going to be my formula which I'm going to use. And here this theta, the theta in the sine theta is not the same as this theta over here. So let me rename this one sine alpha. So basically it means m into v perpendicular times the distance. This is the formula for angular momentum. So let me now make a random time. At a random time, how will the projectile be and what are the angles associated? Let me first draw them. So at a random time t, this is how the image is going to be. The projectile, let it be somewhere over here. Let this be the position vector of the projectile. I'm going to make the projectile in red so that we can see where it is. Let this be the position vector of the projectile r of t. As this varies with time, so let us express it as a function of time, r of t. And now let the velocity also make another angle. Okay, let this angle be alpha. Let the position vector make an angle alpha with the horizontal at all times. Alpha is again variable. Alpha also varies with time. So now let us I'll make this in blue. Let the velocity, see, the position vector and the velocity vector make different angles except for when it is launched. They make different angles with the horizontal. So I'll make another horizontal over here. So this is my second horizontal. This is also horizontal. So let the velocity vector, this is the velocity vector as a function of time. Let this make an angle beta with the horizontal. Even beta varies with time. So now for geometry, I'm going to extend this. So by geometry, we know that the yellow angle which I'm marking, this yellow angle is going to be alpha and this blue angle is beta. So what will the green angle be? Let the green angle be gamma. So what will gamma be? So we can see that gamma is going to be alpha, the whole green thing, the whole yellow thing minus the blue thing. So gamma is going to be alpha minus beta. This is one of the relations which we have. Let us keep this aside. Now how do we find for angular momentum we need to find the perpendicular component of the velocity, which is perpendicular to the position vector of the projectile at that given time. So how do we find? So our velocity vector is the blue line. So how do we find the perpendicular thing? I'm making it in dark blue. This is the vector which we need. Hope you can see this in the black. This is the vector which we need. This is the velocity perpendicular. Even this varies with time. So how do we do? So let us just resolve our original vector into components. Original velocity vector. Resolving it, we get, I'm just going to make this image again over here. So this is our r bar, our v bar. This is the horizontal. I'll make it in white. This is the horizontal. Yeah. So, and this is gamma over here. We want the vector per component of the velocity which is perpendicular to the position vector. So that is going to be basically v sine gamma. And but we know that gamma is equal to alpha minus beta, right? As gamma equal to alpha minus beta, so we get velocity perpendicular, even this varies with time, everything here varies with time, is equal to velocity, the regular velocity vector, times sine of gamma, which is sine of alpha minus beta. Okay, this is one of the equations which we have. So we have achieved this part. Now we need to find the position vector, magnitude of the position vector, with even that varies with time. So what will the magnitude of position vector be? So that will basically be, so magnitude of the position vector as a function of time is going to be the square root of the horizontal displacement plus the vertical displacement. So what will the horizontal displacement be? Again, everything varies with time. So horizontal displacement varies with time, such as u cos theta, which is the horizontal component of the velocity, times into t. So u cos theta into t. This theta is this theta at which the projectile was launched. This is u cos theta into t, and the vertical position of it is given by u sin theta. We know, right? S is equal to ut plus half at square. We know this. So we here u is going to be the perpendicular component, that is u sin theta times t minus g. As g is acting downwards, it is opposite to the velocity, so we are going to represent it with a negative sign, g by 2 into t square. Okay, so now let us square these and find the magnitude of the position vector. We get rx square is going to be u square cos square theta t square, and squaring this, let us use a plus b whole square. We have a square, which is u square sine square theta t square t square, minus 2ab, which is minus 2 u sine theta, and t, there we have a t here and we have t square here, so it's going to be t cube into g by 2. So this 2's cancel, I'll just remove them for the sake of space. Okay, the 2's cancel, we have this, and then plus b square, which is plus g square t power 4 by 4. So, and whole thing is under root. Okay, let me, whole thing is under root, power 1 by 2. So we have, if we take u square t square common from the first two terms, we get u square t square, and we have sine square theta plus cos square theta, which is just 1. So we have finally u square t square minus u sine theta t cube g plus g square t power 4 by 4, whole thing is under root. This is how the magnitude of the position vector varies with time, and this is as a function of time. Okay, now we have this also. Now what we are going to do, so now we have achieved even this, but we know here we just got this in terms of alpha and beta. We know that even alpha and beta are going to vary with time. Now let us see how alpha and beta vary with time. So what is alpha? Alpha is the angle which the position vector makes, angle made by position vector. So we know that if we resolve the position vector into components, it is going to be tan inverse of ry by rx. But we have already derived what rx and r by r. So from here we already know what ry and rx are. So we get alpha as a function of time is equal to tan inverse of u sin theta t So I'm just going to take the LCM over here and put it in the whole fraction. 2u sine theta t minus gt square, this is r by 2, this is ry, and we have by rx, which is u cos theta t. So this is alpha, how it varies with time. Now let us see how beta, how beta, what is exactly beta? It is the angle made by the velocity vector with the horizontal. So now let us see how beta varies with time. So we get beta, we know that beta of time, again if we resolve the velocity vector into components, is equal to Vy by Vx, tan inverse of Vy by Vx. Now let us find Vy. What is Vy? So we know that V equal to U plus AT. So as we know that V is equal to U plus AT, here U is U sine theta, the perpendicular component of the velocity, and A is minus G as it's again acting against the velocity. So we get Vy is equal to U sine theta minus GT. Now what is Vx? We know that for a projectile, if there is no air resistance, we are assuming no air resistance in this case, the horizontal component of the velocity always remains constant, which is u cos theta. Vx is always u cos theta, it doesn't vary with time. So we get beta of as a function of time is equal to tan inverse u sine theta minus gt, that is Vy, minus gt divided by Vx, which is u cos theta. So yeah, now we got that. So now I think we have all the things required for the angular momentum. So we have m is constant, we have m, and velocity perpendicular, we got alpha, we got beta, and we also got beta. Now we need to find v of t here. No, this part is still remaining, we didn't find it. So what is the magnitude of the velocity? What is the magnitude of velocity as a function of time again? This is going to be the same way we did for the magnitude of the position vector, is Vx square plus Vy square under root. Okay, now let's solve for this. So okay, yeah, so Vx is going to be u cos theta, so Vx square is going to be u square cos square theta, and Vy square, let us use a minus b whole square again, that is a square, which is u square sine square theta, minus 2ab, which is minus 2u sine theta gt, plus b square, which is plus g square t square. Again we can see here that if we take u square common, we have cos square theta plus sine square theta. So finally we are left with magnitude of position of velocity vector as a function of time is u square plus u square minus 2u sine theta gt plus g square t square, this whole thing, or 1 by 2, which is under root. Now let us see if we have solved for, if we have all the required things. So we have mass of it, we have the magnitude of velocity vector, we have the we know the value of alpha and beta as function of time, and for the position vector, yeah, we know the magnitude of the position vector also. Now we can find the angular momentum, we can derive an expression for it. So we have okay, I'll do this in yellow again. Angular momentum is equal to mass times velocity perpendicular. The perpendicular component of the velocity is the magnitude times the sine of alpha minus beta. Okay, this is going to be a long expression. Is going to be the magnitude, which is under root of, okay, which is the square root of u square minus 2u sine theta gt, u square minus 2u sine theta gt plus g square t square, gt plus g square t square. This is the magnitude of the vector. Now we need to find the sine of alpha minus beta times, I'll do this in a different color so that's clear enough. I'll do this in red, times sine of alpha minus beta. Now what did we derive alpha as? So we derived alpha as tan inverse of 2u sine theta t. So we have tan inverse of 2u sine theta t of 2u sine theta t minus gt square by 2u cos theta t. This is we are still in alpha. Now we need to subtract beta from this. I'll use square brackets here just to ensure that there is no confusion at all. Square brackets, alpha. Now beta is, now we can get beta from here. This is beta minus tan inverse of u sine theta minus tan inverse of u sine theta minus gt by u cos theta. Okay, now we are done with the velocity part of the angular momentum. Now we need the position part of it. Magnitude of position vector, where did we do it? Yeah, it's right here. So I'm just going to put it there. Okay, it's not working out. Times, okay, I run out of some real estate over here. I'm just going to write it under times, what was the magnitude? These expressions are so long, I need to go back and look at them each time. So u square t square minus u sine theta t cube g. So we have u square t square times under root of u square t square minus u sine theta t cube g. And what was the last term? It was plus g square t power 4 by 4 plus g square t power 4 by 4. Alright, this is a pretty long expression for the angular momentum of this projectile. So yeah, to sum it up, this is what we finally get if we are solving for the angular momentum of this projectile as a function of time. And we are done. But now this is a very lengthy method. I know of one more very easy method, but the answer is there is going to be a very short answer. I think if we simplify this enough, simplify the tan inverse over here, and also take stuff out from the square roots, we should reach the other answer. So now let me tell you the other method which I use. So this is a method. Now let's do it in the second method. So we'll use a bit of integration in this and torque and all. So yeah, so our projectile is going to be at a time t. This will be the position vector of it, and we know that the only force acting on it is mg, which is always downwards, mg downwards, and this is our alpha over here, alpha. I'll make a perpendicular over here. Yeah, this is perpendicular to r bar, so even this will be alpha. Okay, so now let us find the torque on the projectile as a function of time again. So this is going to be very easy. So since we know that torque, magnitude of torque is given by force into perpendicular distance, force into r sine theta, or we can also use, this is not the vector cross product, this is a regular mathematical just product, it's not vector cross product. I'll just remove it. I'll just write it as FR sine theta. Force times the perpendicular distance, or we can also use over here perpendicular component of the force times the regular distance. F sine theta r doesn't make a difference unless we want the vector form. So yeah, looking at this again, if I use the perpendicular component of the force, it's going to get very messy over here. I would need f cos alpha and all. It's going to get messy. So let me use fr sine theta. You will see in a short time why. So yeah. So our f is always equal to mg. So this is magnitude of torque is equal to f is always equal to mg, and the perpendicular distance. What is the perpendicular distance of a projectile, like of the force? Mg is acting downwards. So from this point to this point, what is the distance? It is just the horizontal displacement of the projectile up to that time. So this distance it varies with time. It is given by u cos theta times t. So u cos theta t. Now this is how our torque varies. Torque as a function of time is equal to mgu cos theta into time. Okay, now you must be wondering, what do we do? How do we find angular momentum from this? Now we are going to use this concept. We know that torque is equal to angular momentum, rate of change of angular momentum. This is going to be helpful to us. Now let us rearrange this equation. We get dl is equal to torque into dt. So integrating this on both sides, we get angular momentum is equal to the integral of torque with respect to time. The integral of torque with respect to time. Now we have the torque as a function of time over here, so we just have to integrate this with respect to time so that we get instantaneous angular momentum. So now let us integrate this on both sides. So we get angular momentum is equal to, let us integrate with dt into dt into dt. I'll get rid of this as a function of time thing. Just multiply with dt on both sides and integrate it. So we have angular momentum is equal to mgu cos theta and all are considered a constant when you are integrating with respect to t. So we are left with 1 by 2. We know that integral of t is just t square by 2. T dt integral is t square by 2. 1 by 2 mgu cos theta t square by 2. So this is also what we get. Now hopefully, if we simplify this equation, if we apply manipulation and all, we should be reaching this simple formula. And yeah, if we are specific about the vector forms, now let us go and look at the image again. So yeah, our position vector is in somewhat like this, and velocity vector, I'll make it in blue, it's somewhat like this, in this way. They're not in the same direction. Yeah, if we apply the right hand rule of this, and the vector form of angular momentum is given by m into r cross v, this r bar cross v bar. So if we apply the right hand rule on these two vectors, we can see that we have to move our fingers this way. So this is done only when our thumb is pointing into the screen, which is into the plane. So we know that the direction of the angular momentum vector is going to be into the plane, which is minus k cap. So now let me also mention the direction over here finally, as we are writing it in vector form. So it's going to be this thing. Into the screen is minus k cap direction, we all know that. So it's going to be minus k cap. So So finally, this is the angular momentum of the projectile with respect to time, and we are done.